Jnanam Paramam Dhyayam. Knowledge is supreme.
Let's start with the second part of the fourth tutorial. This part again we will have we will use the Bryan-Ket notation to solve the energy eigenvalue problem, to calculate the eigenvectors, energy eigenvalue and things like that. So, just a quick recap. This is a Ket notation and this is a Bra notation. So, you are already familiar with this angular brackets, okay, which are for Bryan-Ket notation. And let us move on to problem number 4. We have already seen in linear vector space we calculate the norm of a vector, and we will use this hint in problem 4 that norm of a vector is always greater than or equal to 0. So, for a Hermitian operator is given to you. A Hermitian operator is operator when you take the dagger, A dagger is A. So, you have to prove in this that A square is greater than equal to 0. Expectation value of x square is greater than equal to 0. So, how will I write this? Operator A on psi will be this in Ket notation. Now, the bra of this would be A dagger, and when you take the complex conjugate of you will get a dagger and bra of psi. So, let me write this A square will be written as psi A square psi, correct. Now, you have to use this and the hint I gave you before. So, A square I can write as A dagger A, sorry A square I can write as AA. Now, we know that A dagger is A. So, I can write this as simple. This I can write as, we have seen this, right. So, this we can write as nothing but this will be a complex conjugate to this. I can write this as norm of, and norm of any vector is always greater than or equal to 0. This is one way to do. Another way would be simply you define this as some vector v and do the similar exercise. Okay. Both the ways you can do it. So, we have proved here that this is important and you should remember that A square is greater than or equal to 0. So, the norm of a vector is always greater than or equal to 0. So, we have this. In the fifth problem, a Hamiltonian operator again is given to you. So, a physical state has a Hamiltonian operator H is epsilon I 0 0 0 0 0 minus 1. This is the Hamiltonian operator and initial state is given to you. This is at some initial state 1 by root 5, okay, 1 minus I, 1 minus I and 1, okay. And you are given series of questions on this. So, first question is what are the possible results of the measurement of the system in state psi 0. So, this is one part, and what will be the probabilities of each of the possible values that may be obtained. Then you have to calculate the expectation value of the energy. That is the last part, that is a simple part. We have done problems on wherein we have calculated expectation values of the energy. So, to get started with, we have seen in the previous part that how do we calculate the eigenvalues and eigenvectors. If a Hamiltonian operator or any operator is given to you, you can simply use the energy eigenvalue equation H psi is equal to lambda psi, where lambda is the eigenvalue. So, now you have a 3 cross 3 matrix. You will use the same logic, and the eigenvalues. So, by now you have mastered the way to calculate the energy eigenvalues and eigenvector, this is what I hope, and by looking at the matrix you can guess plus epsilon, minus epsilon and minus epsilon. These are the energy eigenvalues. So, you can see from here that epsilon, minus epsilon are the energy eigenvalues. So, what would this mean? That there are 2 eigenvalues which are minus epsilon. So, you have a degenerate state. Let us go to this operator. H is operated on the eigenvector psi 1 will give me the eigenvalue lambda 1, and it is not difficult. Again you will calculate this. I will give you one example and the rest you can do it by yourself. Again let me call psi 1 as x1, x2, x3, and I have a epsilon here and an epsilon here. Okay. You have here x1 times I is equal to x1 minus I x2 is equal to x2 and minus x3 is equal to x3. You have to solve these 3 and get psi. So, from here you can guess that x3 is equal to 0. Okay. This is the only possible answer. X1 is, oh sorry, you have x2 here, x1 here. So, your x1 is Ix2. Okay. So, your psi 1 will be 1 I 0. Okay. Again I have used here psi star psi 1 star psi 1 is 1 to calculate the normalization factor and the value of x. Okay. So, the normalization factor and the value of x you can get from here. With this you can similarly calculate psi 2 and psi 3. It is a simple task. You have here 1 minus 1 0 and psi 3 will be 0 0 1. I hope you will not have any difficulty in calculating psi 1, psi 2 and psi 3. You have to simply follow this step wherein you will use the energy eigenvalue equation. You have the operator H, you will operate it on the vector eigenvector, and using this you will get 3 equations, you will solve them and you get the wave function, the eigenvectors psi 1, psi 2 and psi 3. It is not a difficult task. Now, the initial state psi 0 was given to us. So, eigenvector the initial vector was given to us as 1 by root 5 times 1 minus I, 1 minus I and 1. Okay. Break psi naught in terms of psi 1, psi 2 and psi 3. Anyways, we have to calculate psi naught. So, I can write this as root 5. So, I can write this as 1 root 2 by root 2. I can write this, right, and I have 1 minus I, 1 minus I 1. Okay. So, this can be rewritten, I can rewrite this as 1 by root 5 into root 2. Okay. Then I can write this as 1 I 0. Okay. This is my psi 1. One way would be to break this in terms of psi 1, psi 2, psi 3. Another way would be, and see what you get. Psi 1, I can write it as 1 by root 5 into 5 by root 2, root 5 by root 2, okay, 1 I 0. Okay. And psi 2 as 1 by root 5, again root 5 by 2, 1 minus I 0. Okay. And psi 3 as 1 by root 5 into root 5, 1 0 0 1. Okay. And now when I add psi 1 plus psi 2 plus psi 3, what do I get? 1 by root 5, okay, psi 1, psi 2, psi 3, when I am adding, I will have, so basically this is 1 by root 2 only, I will have here 1 plus 1, I do not want 1 plus 1, okay, I want 1 minus I. So, I multiply this by minus I. Okay. So, I have 1 minus I and this is 0. So, 1 minus I, next one is I into minus I. So, rather I will have to multiply this by minus I. So, let me multiply this by minus I, this is nothing. So, first term will give me minus I plus 1. So, 1 minus I. Second term will give me 1 minus I. Third term will give me 1. Psi 1. Okay. So, my psi 1 was nothing but 1 and I. So, you will have a psi 1 plus I have 2 by root 2, root 2 by root 5, psi 2 plus 1 by root 5, psi 3. Okay. So, this is what I have. Okay. Now, let us check the factors. So, 2 by root 5, psi 1. So, what was psi 1? Psi 1 we have obtained here as 1 and I. Okay. Psi 1 is 1 and I. So, you will have to multiply this by minus I. So, I have a minus I and the rest goes. Okay. So, we have expressed psi naught, that is the initial state, in terms of the eigen states. Okay. So, this was a simple exercise. It is a lengthy exercise, but a simple exercise. So, you can see the coefficient C1 is minus I root 2 by 5, C2 is root 2 by 5, C3 is 1 by root 2 by 5. Okay, why did I write the coefficient? These coefficient will correspond to the possible, you can calculate the probabilities using this C1, C2 and C3. So, what will be the probability of finding the particle? Okay, remember this set of eigenvectors I have obtained in this manner, you may get a different set of eigenvectors wherein you may have different coefficients C1, C2, C3 may be different in your case. It may be swapped. So, what I am getting as C1 you may get as C2 and vice versa, and this is not a unique solution, this is not a unique vectors. So, you can have different sets of eigenvectors. So, when you try it yourself, just check whether you get a different set of eigenvectors. So, this C1, C2, C3 is what you obtain. Now, in order to obtain the probability on E1 plus probability of E2. So, P of E, let me represent this P of E as the probability of finding the particle in either state 1 or state 2, that is epsilon 1 or epsilon 2. E1 will be corresponding to eigenvalue plus epsilon, E2 will correspond to finding the particle with energy minus epsilon. So, we have a degenerate state for E2. So, this would be simply square this. So, you have minus 2 by 5. So, when I take the complex conjugate, I have plus 2 by 5, and square of C2 will be again 2 by 5, and this will be again 1 by 5. So, I have to multiply this by epsilon and I will multiply this by minus epsilon. So, I have 3 by epsilon, so minus epsilon by 5 is what I get the probability of the possibilities of finding the particle in this and this or this state. So, finding the expectation value is again a simple task wherein you will write the time dependent Schrodinger equation, use the time dependent wave function and then calculate the energy eigen. And remember that energy operator is written as I cross rho by rho t. This is the energy operator. So, using this you can get the expectation value of energy. So, the expectation value of energy you will write, let me give you a hint. Hint would be for expectation value you will write the wave function sin out of t as, you will have e raised to I e t upon h cross upon and psi of sin out of t. So, sin out. Okay. So, you will write the expectation value. So, here you will put the Hamiltonian operator, and when you operate it on the state you will get either E1 or E2, either epsilon or minus epsilon, and then you can easily calculate the energy eigenvalue. And hope that this will make simplify these simplified steps would help you to understand how to calculate, and you need to do it at least once by yourself to understand this properly. And in this problem, in the end you can see here that one thing which we have seen here is that the energy eigenvalues what we obtain, one of them is degenerate and the other one is non-degenerate. So, you can understand that when you find the particle in one state with energy epsilon and the other with energy epsilon minus epsilon, there are two indistinguishable state which are degenerate. So, when you make such measurement, it is difficult to distinguish the two states. So, we will come to more number of problems on these measurements, and then in the pipeline you have more problems on Bryan-Kett notation, wherein you will learn how to write the conjugate basis vector and problems which will involve more on energy eigenvalues, energy eigenvectors. So, this part should be thorough and should be clear before you go to the advanced topics like the Schrodinger picture and Heisenberg picture. So, we are trying to slowly evolve from using the Bryan-Kett notation and go to the evolution picture of Heisenberg. So, in the next tutorial we will continue with more number of problems.